Hello and good morning, and welcome to the new episode, which is directed to AS and A-level candidates. In this episode, I'm going to solve actually two questions, not all of them, because the last question, question 1, is totally similar to the question number 3. So here I'm going to solve only question 3 and these two threes. Okay. These questions are related to the controlling reactions. I mean, with the controlling reactions, how to deal with the reaction by increasing or decreasing the temperature or pressure, and how you are these factors, they will affect on the rate of reaction, the percentage of the yield, the percentage of the product, the yield of the product, in a team of collusion theory. Okay, so let's start with the first question. Okay, so in this question, the hydrogen halides HCl, HBr, and HI can undergo thermal decomposition. In a sealed container, an equilibrium is established according to the equation shown. You have 2 mole of HX produced hydrogen and X as a diatomic molecule. This reaction is reversible reaction. Okay, reversible reaction, and these X, actually chlorine could be bromine or iodine atoms. Some bond energies are shown in the table. The bond energy is measured by kilojoule per mole. For HBr is 366, hydrogen, the bond between the hydrogen atoms 436, and between the bromine atoms in a bromine molecule 193. Use these data to calculate a value for the enthalpy change delta H for the thermal decomposition of hydrogen bromide HBr according to the equation shown. So in the equation you have HBr hydrogen and Br2. Okay, and this one is 2 mole. Okay, always in the delta H equal this one, the bond in between the HBr, it will be broken actually. So here it's you have 2 mole time positive 366, and in the formation you are going to form new bonds, so always it's exothermic. So you have negative for hydrogen for 436, and for bromine you have 193. Okay, in this calculation here you will get the result, which is 103. Just let me check it, please, because I haven't calculated. Is 2 times 366 minus 436 minus 193. So it's positive. Okay, it's positive. So the reaction, it's endothermic reaction, because it's very clear it's decomposition. At a temperature of 700 Kelvin, a sample of HBr is approximately 10% decomposed. Changing the temperature affects both of the rate of decomposition of HBr and the percentage that decomposes. So the Boltzmann distribution for the sample of HBr at 700 Kelvin is shown. EA, which is activation energy, represent the activation energy for the reaction. So here we have Boltzmann distribution use the same axis. Sketch a second curve to indicate the Boltzmann distribution at higher temperature. So, at higher temperature, you need to start from the origin, okay? And in this case, this peak, it will be lower than this one, this curve, lower than the at 700 Kelvin curve, and then it will be shifted to the right. That means here, this one, it will be like this one. So now this peak, it's lower than the previous one, and it will be shifted to the right. Okay, so here in this case, this shaded part, which these molecules, which they have energy more than the activation energy, okay, which their collision is classified as a successful collision, more than the molecules in the previous one. That means at lower temperature. So here, with reference to the curve, state and explain the effect of increasing the temperature on the rate of the decomposition. So rate increase. Why? As the number of collision increase according to the collision theory. Okay, so here you need to explain that, because I'm not going to write the full answer, okay? Just I'm explaining, and you need to write the full explanation. So the rate of reaction is increased. Why? According to the collision theory, the number of collision is increased, okay? Then, according to the curve, the average area above the activation energy at higher temperature, it's larger than the average area which is under the activation energy of the previous one. So here it's very clear, this shaded part at higher temperature, this area larger than this area at low temperature, okay? So here increasing temperature on the decomposition curve, I have explained. So rate of the decomposition, it will be an increase. So we have talked about the rate and the state. We have stated and we have explained that. Sorry, in the explanation, you need to say the number of frequency. Sorry, the number of successful collision. It will be higher in at the higher temperature, and more than the successful collision at lower temperature. So rate, you need to talk about the rate, and you need to compare the curve, which is after the activation energy, between the low temperature and high temperature, and what do we have below this area, which is after the activation energy. It represents what? Actually, it represents the molecules which they have energy, which they have successful collision. So you got 3 marks. The decomposition of HBr is endothermic. It's very clear because it's 103 kilojoule per mole. State the effect of increasing the temperature on the percentage of HBr that decompose. Use Le Chatelet's principle to explain your answer. Okay. Now, your reaction is endothermic reaction. That means your reaction, it's absorb energy, it needs energy. So your reaction, it will be shifted to the right. When it will be shifted to the right, that means the percentage of the decomposition, it will be increased, and you will produce more of bromine and hydrogen gases. So again, I'm going to repeat this part. According to the Le Chatelet principle, you need to explain the answer. So first of all, you need to explain your temperature. It's endothermic. What does that mean, endothermic? Endothermic, that means your reaction needs energy, will absorb energy, will absorb heat. So by increasing the energy or the heat, your reaction, it will be shifted to the right side. Okay, according to the Le Chatelet principle. According to the Le Chatelet principle, when the reaction, it will be shifted to the right, that means your reaction will be decomposed more, and you will produce more of a product, which are bromine and hydrogen. Okay, so these things that I have explained, you will see all of them in the mark scheme, which is attached to this video. At 700 Kelvin, HBr is approximately 10% decomposed, but hydrogen iodide is approximately 20% decomposed. Now explain this difference with reference bond strength and the factor that affect them. So you have here 1 mark, and you need to explain 2 factors at least to get 3 marks. So first of all, if you will compare the bond strength of Hi with HBr, you will see the amount of energy which is required to break down the bond between HBr. It's more than the amount of energy which is required to break the covalent bond between H and I. This is 1 mark. Why we have this difference in the bond energy between the HBr and Hi? Due to the reactivity of the bromine atom. Bromine atom is more reactive than iodine atom. Why it's more reactive? Because the size of bromine is smaller than the iodine. So because it's small, that means the force of attraction between the nucleus and the covalent electrons, it will be stronger than the force of attraction of the force of attraction between the nucleus of iodine atom and the paired electrons. What I mean with paired of electrons? I mean the electrons which are shared in the bond energy. That means here you have, for example, Hi. This pair of electrons, actually these pair of electrons are attracted to the iodine. Why it's attracted to the iodine? It's clearly you'll say because iodine is more reactive. Why it's more reactive? Because the force of attraction between the nucleus in the iodine, okay, attract these electrons. So I mean this force of attraction. Okay, so you will get the 3 mark for this question. Question C. At temperatures above 1500 Kelvin, HCl will decompose. A sample of 0.3 mole of HCl decomposed in a sealed container. The resulting equilibrium mixture was found to contain 1.5 times 10 power minus 2 mole of chlorine. Now question, calculate the amount in mole of hydrogen and chlorine present in the equilibrium mixture. Now this one. HCl decompose hydrogen and chlorine. And here. At the beginning of the reaction, you put only 0.300 mole. Before starting your reaction, here you have 0, 0. At equilibrium, the resulting mixture found 0.5, 1.5. That means with this power minus 2, that means you have 1.5 over 100. That means at the equilibrium, chlorine it's 0.015 mole. Okay, why? Because this one 0.300 minus 2x, and this one x, and this one x. So x is equal to 0.015. So this one, it will be same. What about this one? This one, it will be 0.300 minus 2 times 0.05. And this one will give us 2.7. So for HCl, 0.27, and for hydrogen, same number of mole of chlorine. Why? Because according to the balanced chemical equation, you have equimolar. Okay, that means same number of moles, same ratio. Now calculate the mole fraction of each gas in the equilibrium mixture. Mole fraction, that means at equilibrium, how many mole total? How many mole? Mole fraction. Total, the total number of mole, actually it's 0.3, because 0.015 plus 0.015 plus 0.27, this one 0.3. Now let's calculate for HCl, this one 0.27. So 0.27 over 0.3, this one you will have this fraction of mole, 0.9. Okay, so then the mole fraction for the hydrogen or chlorine, 0.015 over 0.3. So 0.015 over 0.3, this one will give us 0.05, and the same for chlorine. In another experiment, under different conditions, an equilibrium mixture was produced with mole fractions for each species as shown. Write the expression for the equilibrium constant Kp for the decomposition of HCl. Here the expression, product over reactant, so H2 times partial pressure of chlorine over this one for HCl power 2, because you have 2 mole. This is the expression. Explain why the total pressure of the system doesn't need to be known for Kp to be calculated for this experiment. Let's come back to the balanced chemical equation. In the balanced chemical equation, you have in the reactant 2 mole, and in the product 2 mole. So here 2 mole and here 2 mole. That means here both of the sides of the reaction have same number of moles. So increasing or decreasing the pressure here has no effect on the equilibrium reaction. Okay, so here we don't need to know the total pressure to calculate the Kp. So here you will deal with these fractions of mole directly to calculate the Kp. So here you need to say, because the number of moles of reactant and products are equal, so there is no effect of the total pressure on the equilibrium of reaction. So to calculate the Kp, you have 0.06 times 0.06, 0.06 times 0.06 over 0.88, but this one should be squared. Okay, and the result actually I haven't calculated, but then you may calculate this one to get the Kp, and there is no unit because Pascal or mole, it doesn't matter, they will cancel each other, so at the end here you have no unit. In the question 3, the next question, sulfur trioxide, here you have SO3 is manufactured from sulfur dioxide and oxygen by the contact process. The reaction, it's given here, and the delta H, it's negative 196 kilojoule per mole. That means your reaction is exothermic. The enthalpy change of formation of SO2 is given, which is negative 296.8 kilojoule per mole. Define the term enthalpy change of formation. Enthalpy change, the amount of energy, which is enthalpy, okay. The amount of energy, because it's formation, that means you will produce the amount of energy which is produced to form 1 mole, of the product of the compound. From where? From its element. Okay, from its element. At which state? At gaseous state. Okay, so you need to focus on these 3 things. You have to produce 1 mole, okay, from its element at gaseous state. Use the data to calculate, the next question, use the data to calculate the enthalpy change of formation of SO3. Here, formation of SO3. Now, as we have learned that, now, SO2, it's not in the formation part, okay? It's not in the formation part, so it's in the reactant, so you will say 2, and the negative, it will be positive 296.8. Okay, oxygen, you don't need to know the delta HF of oxygen because already it's element. Okay, then SO3, it's already formed, so here you will take it as a positive because plus, okay, plus. What's the sign of formation? Always in the formation, always you have negative. Why? Because formation of any compound, it will be exothermic. So here you have 2x, and this one give us negative 196. So here at the end, just you need to find, minus 2x. Then just you need to find x, and this x, it's represent the amount of energy which is required to produce 1 mole of SO3. Next question, the contact process is usually carried out at temperature of approximately 700 Kelvin, a pressure of approximately 150 kilopascal, and in the presence of vanadium oxide as a catalyst. The Boltzmann distribution for a mixture of SO2 and oxygen at 700 Kelvin is shown. EA catalyst, that means the activation energy for the catalyst pathway represent the activation energy for the research in the presence of the catalyst. Okay, now this is a question. Add a labeled mark of activation energy without catalyst. So without catalyst, that means here should be on the right of the activation energy in the presence of catalyst. So here it's EA and catalyst. Okay, why? Because and you will see here in the next question, state the benefit of using a catalyst in this reaction. Explain how it's achieved this effect. Okay, so by adding the catalyst, you have decreased the level energy of the activation energy. Okay, so as you have increased the level of the activation energy, in this case the shaded part or this area becomes more than the area without catalyst. What does that mean? That means the molecules that they have successful collision becomes more. Okay, so the rate of reaction, it will be increased as you have successful collision. So as a result, the reaction, or the according to the balanced chemical equation, your reaction, it will be shifted to the right by producing more of SO3, or you can say the percentage yield of SO3, it will be increased. So let's come back to this question. You need to state benefit using the rate of reaction, it will be increased. Why? Because the number of collision, it will be increased. How that increase? By decreasing the level of energy of the activation energy. Okay, activation energy, so you will have more successful collision. State and explain how an increase the pressure would affect both of the rate of reaction and the yield. So here you have rate and yield. Okay, so you have 4 marks, so that means you need to 2 for this one and 2 this one. Now the rate of reaction, it will be increase. This is 1 mark. Why? Because the number of collision, that's okay. So again, 2 mark for this one and 2 mark this one. Now the rate of reaction, it will be increase. Okay, the rate of reaction, it will be increase. Why? Because the number of collision between the particles, it will be an increase. The yield, why it's an increase, the yield? And if you have a look to the reaction, you have 3 mole. The yield, it will be increased. Why? Because according the number of moles in the reactant side, it's more than the number of mole in the product side. So increasing the pressure, according to the Le Chatelet principle, the reaction, it will be shifted to the right, so more product, and the percentage yield, it will be increase. Okay, so here you will see the full answer in the mark scheme, but I'm explaining these main points. At this pressure, which is 1.5 times 10 power 5 Pascal, and 1 mole of sulfur dioxide gas was mixed with 1 mole, here 1 mole, here 1 mole of oxygen. The final equilibrium was found to contain 505 mole of oxygen. So before the reaction, you haven't produced SO3. At the equilibrium, this number of mole of oxygen found, it's equal to, okay, and this one we don't know, and this one also we don't know. So in this case, 1 minus x, and this one 1 minus 2x, because 2 mole you have, and you have formed 2x. So you need to find the value of x. 1 minus x equal to 505. So 1 minus 0.505. So x equal 495 0 point. Okay, so the number of mole of oxygen, this number time 2, so you have 0.99, and this one 1 minus 2x. 2x already it's 0.99, so here this one it's 0.10. Okay, to make them as the same number of significant, this one 0, here this one 0. Okay, so the number of mole of SO2, this one 0.1 mole. Okay, and this one it will be 0.99. Now calculate the partial pressure of oxygen gas. Partial pressure, you have the total pressure, partial pressure equal fraction mole fraction of oxygen. So here you have 0.55 over this one plus this one plus this one 1 over 1505, and this one will give us 0.335. This is the partial pressure, the mole fraction of oxygen time the total pressure. Total pressure, it's 1.5 power 1.5 10 power 5, and the unit it's Pascal. Yes, Pascal. Just you need to find the result, and you write it here. In another experiment, mixture formed from different starting amounts, SO2, O2, and SO3. Okay, you have the partial pressure for all of them. You need to write the expression. Okay, according to this expression, you have 2 mole of SO3 product over reactant, SO3 power over SO2 power time oxygen power 1, because 1 mole. Then you need to calculate the Kp. For SO3, this one, power 2, and for SO2, this one 8.42 power 2, this one should be square, time for oxygen 6 time power 4. Okay, you will get the Kp, but you need to find the units. So here the unit actually Pascal square for this one, Pascal square, and this one Pascal square time Pascal. This one will cancel this one, and you will have Pascal power minus 1. So you'll have a look to the next question. Here this one, it's totally similar to the previous one. Here just you need to find the bond energy for this one. You need to show your working in this part, okay, and you need to explain the bond energy, which is the amount of energy which is required to break the 1 mole of covalent bond at a gaseous state. Here this question, it's the same. You need to using the same axis sketch a second curve to indicate the Boltzmann distribution at higher temperature, which is totally similar to the previous one. So the peak, it will be lower than the previous one, and all the curve, it will be shifted to the right. Here, according to the Boltzmann distribution, you will explain why the temperature affecting that temperature is effect on the rate of reaction. Here then you need to find the number of mole. You need to write the partial pressure by finding mole fraction of ammonia, then you will multiply it with total pressure. Then you will calculate the Kp. First of all, you need to write the expression, then Kp, then you will find the value of Kp with its unit. Here, affecting on the yield here. Okay, so it's totally similar to the question number 1. So by the end of this question, I would like to thank you for watching and listening this episode. So see you in the next episode with next topic question. Bye.